Okay, let's continue with our capacitor discussion. Now you guys know that capacitors, the charge storage devices, electrical charge storage devices with so many other applications. We will eventually talk about these applications. They act like batteries, rechargeable. You can take an empty capacitor, connect it to a battery, a DC battery. It has to be DC. Some voltage like 1.5 or something. It has to be DC because the reason is when you charge the capacitor this way, one side gets positive, the other side gets equal amount of negative. If you connect it to an AC supply, alternating voltage, the current is going back and forth, so at every cycle it will charge in opposite direction, so the capacitor is going to be charge, recharge continuously, and there is no real use. We can't use it for anything. It won't hold any charge. It's charging and discharging back and forth. But capacitors are used in AC with AC signals, with AC currents as a filtering device. That's a electronic application. We might not go that far in this class, but yeah, for us we use it with DC batteries. Okay, so in a circuit, when we connect a capacitor, let's say the capacitance is C, we know that it's going to accumulate amount of charge equals to C times V. And also we talk about how to find the capacity of a parallel plate capacitor when we know the plate area and the separation and all the physical dimensions. Okay, so let's say we have a circuit and we want to change the capacity, right? We can do that by adding multiple capacitors. Instead of one capacitor, we can add 2 or 3 more capacitors. That change the capacitance of the entire circuit. There are 2 ways to do that. One is the series, like multiple capacitors, right? One way is adding capacitors in series. Series combination, we talked about this some time ago. Series means one behind the other. Like you have one capacitor here, you're going to add another one, so we can label this as C1, the first capacitor, and then you connect a second capacitor C2 and a third capacitor C3, and then we can connect to a battery. So this is a combination of multiple capacitors. We can add them parallel. Parallel means the left side of all the capacitors connect together, the right side of all the capacitors connect together. You see the difference over here. The right side of the first capacitor goes to the left of the second one. Right of the second one goes to the left of the first one, or one in front of the other one. So this is the series combination. Parallel means, let's say we have 3 capacitors, C1 and erase that, C2. So the parallel, we can easily draw them one underneath the other one. So here's C2 and here's C3. We can connect all these left sides together into a one connection and all the right sides together, and then connect to the rest of the circuit. Like you can put a battery here. So the positive side is common to all these sides, the negative side is common to all these sides. So that's a parallel connection. We can draw parallel something like this. So here's the capacitors. 3 capacitors, we can connect all of them like this. This is still the same thing, right? All these left sides are connected here, same thing. All these left plates are all connected into one line. That's a parallel connection. and then we can connect the battery like this, and the battery is also parallel with all three, right? The left side of the battery is common to all these capacitors left side. We can have combinations. Sometimes in circuits we have to add series parallel combinations. So depending on how we connect them, whether it's series or parallel, the total capacity, total capacitance, sometimes we call CEQ, equivalent capacitance. This changes depending on these numbers, like how big these capacitors are and what arrangement we have. Okay, so that's what we're going to discuss. How to find the total capacity when they're in series, when they're in parallel, and when we have mix of everything. Okay, so let's clear this. So that's our goal, finding series parallel total capacities. Let's go to the next slide. Capacitors, series and parallel. So we're going to start with parallel combination. Let's see how to understand what's going on here. Let's say we have three capacitors like in this diagram. C1, C2, C3. And we're going to connect all that together, and then all these also together. Now the three capacitors are in parallel, and then we connect it to the battery. And the battery voltage is V. Now when capacitors are in parallel, this is something you should remember. If the capacitors are in parallel, C total or C equivalent is the sum of the three capacitors. So if you have 5 capacitors in parallel, you add all 5, right? So for an example, let's say C1 is 10 microfarads, this is 20 microfarads, this is 30 microfarads. CEQ is 10 plus 20 plus 30, which is 60 microfarads. That's CEQ. So it is same as replacing all three with a single capacitor and connect to the battery. This capacitor should be 60 microfarad. It will accumulate the same charge. It will work exactly the same way. Right? So that's the idea of equivalent capacity. So the equation is, if the capacitors are parallel, it's pretty simple. You add the numbers. It can be if it is two capacitors, you just add the two numbers. How to get to this equation? There is a proof. Maybe I'll show it when we discuss in class. It's not that difficult. The voltage, something to remember, when the system is parallel, when all these things are parallel to the battery, the same voltage appears across each capacitor. It's like you take the multimeter and you measure the voltage here. Let's say the battery is 10 volts, 10 will appear here. You take another multimeter and measure the voltage here. That will be 10. So each each capacitor gets the same voltage. So each capacitor will have the same charge. And also you know that charge separation, how it works, one side positive, one side negative. So combining all that, we can come to this equation. We'll talk about it some other time, maybe in class. But what you need to remember is, if the capacitors are parallel, this is the equation. Alright, let's move on. Alright, What about capacitors in series? Let's take a new page. As shown in the diagram, let's say we have three capacitors in series. C1, C2, C3, connect to a battery. What is the total? Now when the capacitors are in series, it's a different formula. We need to find the total capacity of all three, right? C equivalent. Now we can't directly find it. We can, but the way we're going to do it is, instead of finding the C equivalents, first we calculate 1 over C eq. The formula for that is 1 over C1, 1 over C2 plus 1 over C3. If you have more capacitors, let's say the fourth one, you will add it as 1 over C4. So you do this math first. Once you have an answer, then you go back and find CEQ. Alright, so these are two things to remember. If they are parallel, you just add the numbers. If they are series, you add them as the reciprocal. 1 over the number, we call it the reciprocal. So you add the reciprocals and then turn it upside down and find the answer. So let's try a simple example here. Let's say this is again 10 micro, 20 micro and 30 micro. So we need to find CEQ. This is the question. What we do is we find this first, 1 over CEQ. So we write it as 1 over 10, 1 over 20, 1 over 30. Since everything's in microfarads, you don't need to worry about 10 to the negative 6. You can add them as microfarads and later find, once you have the final answer, convert it back to farads if you want to. But let's do it this way. So, if you are comfortable with simple algebraic operations, you can look for the common denominator for all these three. It looks like the common denominator is 60. So we can write 6 over 60. 1 over 10 is 6 over 60. 60 over 3, right? Yep. Plus 60 over 2. Now we wrote everything with a common denominator 60, and then it becomes just 60 under the line, 6 plus 3 plus 2, which is 60, 11. Now this is 1 over CEQ. Still not the answer, right? So what is CEQ? So because of that, CEQ, equivalent capacitance, is 60 over 11, which is 555. I think so. Let me try the calculator. 60 divided by 11 gives me 5.45 microfarads. So the equivalent capacitance, if you want to replace all three with a single capacitor, you have to put C equals 5.45 microfarads. So it's important to remember, when it is series, this is how you start, and then after you complete all the math, take the reciprocal and find the equivalent capacitance. So you might ask, why would you keep adding multiple capacitors? Why can't we just use a single capacitor? Well, that's not the case. That is also a reason, but in actual circuits, like if you take a circuit board, like for an example, a computer motherboard or a processor, there's like millions of tiny little capacitors here and there everywhere. Like a memory chip will have a million, sometimes couple of millions of capacitors just for the memory part. So we need to know the total capacity of these kind of things. So these are the kind of formulas we will use. In a neural network, you map the human brain. it creates different capacitance here and there because of these electrically conducting neuron cells. So knowing the capacitance is important to understand the function. So how do you find the total capacity? This is the formula you will be using in a much advanced way, but it's the same math, right? This is how it works. Okay, so going back, let me clear this real quick. So what you need to remember, the parallel system, something like this. This is a parallel system. C equivalent is direct sum. If you have more, you can add them. A series system, one behind the other. You start here. And if you have more capacitors, you add them. Once you have this, you take the reciprocal of this and find the answer. Okay, so that series and parallel capacitors. Next thing is, what if we have a combination of series and parallel? Let's see what the next slide says. Determine the capacitance of a single capacitor that will have the same effect as the combination shown. Okay, so what we have is two capacitors. In this case, we don't need the battery to find the answer. We're just asking what's the capacitance is. So I'm going to remove the battery, right? So this is all we have between A and B. This is point A. This is point B. Between A and B, let's say all these capacitors are equal. C1, C2, C2 here, C3 here. Actually, no, let's put different numbers. Let's say C1 is 10, C2 is 20, 3 is 30 microfarads. One more thing, going back here, if the capacitors are parallel, you see that the equivalent is the sum of the capacitors. So CEQ or C total will be bigger than any of those capacitors because it's a sum. Over here, if you actually check the math carefully, CEQ will be less than any of the single capacitors, right? It will be smaller than the smallest capacitor. Over here, in the parallel system, the total will be bigger than the biggest capacitor. So these are certain things that if you remember these, it makes it easier to to see whether you have done a mistake. Alright, so our question is, what's the total capacity C total between A and B? What kind of single capacitor can we use to replace this entire system? So how do we find the total? This is how do we analyze this? Now in situations like this, we have to go section by section, step by step. Look for simple arrangements. Here you see the two capacitors C2 and C3 are parallel. And the sum of these two, C2 and C3 total, is in series with C1. So we're going to work with C2 and C3 first. They're parallel. So for C2 and C3, they're parallel. So parallel means you can just add them. C total is C2 plus C3. So that will be 20 plus 30, that will be 50 microfarads. Let's call this whole thing C23, right? It's like I'm going to replace this with a single capacitor. So here's the point A. Instead of this combination, I'm just going to put a single capacitor, which is C23, which is 50. And then after that, right, so if we call this X and Y, this is that point X and Y, right? There were two capacitors. I remove them and I put a single capacitor. After that, we have C1 and then point B. Now you see this C23 and C1 are in series with each other. So let's see. Now my next C total, then this is my grand total, this whole thing and this one in series. So I'm going to write it as 1 over 50 plus 1 over 10. So I can get a common common denominator, which is 50, 1 plus 5, 6 over 50. So my C total or CEQ is 50 over 6. 8, 48, 20.33 microfarads. 8.33 is my CEQ. Okay, so we can try. I mean, these questions can be very creative. You can add capacitors in any order we need. But this is the thing to remember. You start with small sections and expand. And also, if you are not comfortable with this common denominator thing, just use the calculator. So let me show you how to do that. I'm gonna clear this. So we have, what we had was 1 over CEQ is 1 over 50 plus 1 over 10. So use the calculator. Find what is 1 over 50 is. So it will be 0.02, I think. 1 divided by 50 is 0.02. Find what is 1 over 10, which is 0.1. Add them together. 0.12. This is 1 over CEQ. So 0.12. And then CEQ is 1 over 0.12. So 1 over 0.12, 8.33 gives you the same answer. Okay, all right. So I'll give you guys an exercise to do. We'll discuss more in class. Let's try this. Okay, this is point A, this is point B. Find the C total or equivalent between A and B. Let's put some numbers. Let's say 10, 20, 30, 40 microfarads, all of them are microfarads. Find the total capacity. Alright, you guys give this a try. We'll discuss more in class. Okay, thanks everyone.